Hey guys, welcome to Safi Mixed. In this video, I continue from where I left in the video part 1 on the topic particle in one-dimensional infinite potential well, where I discussed the classical solution of the problem. So I would suggest you to must watch that video because there I elaborated on the importance of discussing this problem in every introductory book on quantum mechanics. Here in this video, I want to find a solution to the problem from the perspective of quantum mechanics and would compare the results of classical and quantum solutions at the end of this video. Remember, the quantum mechanical solution to this very simple problem gives insight to the understanding of quantum mechanics of complicated many particle systems. Let me begin by first borrowing the pictorial representation and the mathematical expression for the potential of infinite potential well from the video part 1 on this topic. So here it is. This is the pictorial view of an infinite potential well, and I have discussed this in detail in the video part 1. And this is the mathematical relation for writing the potential function of an infinite potential well. So without repeating further detail of this equation, I would just say here that A in this equation represents the width of the well. Now I would like to write down the Schrodinger wave equation for a particle of mass m and total energy E in a region of potential Vx, which is given by this one equation. Now let us discuss a little physics related to this equation. This equation is physically meaningless only when every part of it is finite. Otherwise, it loses its physical significance. With this in mind, if we look at the second term on the left, it is a little problematic in the present scenario because according to equation 1, outside and at the boundaries of the well, the potential Vx equals infinity, which would make this part infinite at the boundaries. So to keep the second part on the left of this equation finite and the equation retains its physical meaning, we conclude that the product V of x times psi of x times equals 0. On the boundaries, this result is possible only when the wave function goes immediately to 0 at the boundaries. This concept physically agrees with the structure of the problem because the existence of wave function outside the well would mean the existence of particle outside the well. And this is conceptually not possible for an infinite potential. So the bottom line is this: the wave function vanishes at the boundaries of the well. You must note this property because this is a very important concept related to the wave function. Also, inside the well, as equation 1 dictates, Vx equals to 0. Therefore, setting the second part in the Schrodinger wave equation on the left equal to 0, the Schrodinger wave equation reduces to this simple form. That is minus h bar square divided by 2m d square psi of x divided by dx square equals E psi of x. And taking minus h bar square divided by 2m to the right side of the equation, I can further write the equation into this form, that is d square psi of x divided by dx square equals 2me divided by h bar square psi of x. Equation 3 can be put into another simplified form if I define a quantity k such that k equals the square root of 2 times me divided by h bar square, or k square equals 2me divided by h bar squared. With this substitution, I can put the equation into d square psi of x divided by dx square minus k square psi of x, and taking the right side to the left, I can further modify the equation into this form. This is very familiar second order differential equation whose roots equation takes the form d squared plus k squared equal to 0, and solving this for d, I get d equals plus minus iota k. And we know from our courses on differential equation that for each root of a second order differential equation, we either have an exponential or sinusoidal solution. So according to equation 6, we can have two possible solutions to equation 1. But according to the superposition principle of quantum mechanics, the most general solution is a linear superposition of the two possible solutions. If instead of an exponential solution, we go for the sinusoidal solution of each root, then the general solution can be written in the form psi of x equals a times sine of k times x plus b times cos of k times x, where in the present form a and b are two arbitrary constants whose values can be determined from the boundary conditions. So we have two boundary conditions, one at x equal to 0 and the other at x equal to a, and as discussed above, the wave function vanishes as these boundaries, that is, we have psi of 0 equals psi of a equals 0. Equation 8 defines the two boundary conditions for the problem. So let us put these boundary conditions one after the other into equation 7 and see what happens. First, setting x equal to 0 in equation 7 gives psi of 0 equals a times sine of 0 plus b times cos of 0. With reference to equation 8, the left side of equation 9 is 0. And on the right, only the first terms goes to 0 because sine 0 equal to 0. However, cos 0 is 1. But the left and right sides of equation 9 must agree. And this is possible only if the constant b on the right side multiplying with the cos function is 0. So the first boundary condition leads us to choose b equal to 0. With this choice of constant b, equation 7 reduces to psi of x equals a times sine of k times x. Equation 10 is a little simplified form of the solution for a particle inside an infinite potential well. But wait, we are still not completely done, as we can find one more condition on k by using the second boundary condition of equation 8. So setting x equals a in equation 10, we get psi of a equals a times k sine of k times a. Again, according to equation 8, the left side of equation 11 is 0. The right side must also be 0. Here, two cases arise. Either the constant a is 0 or the sine function could be 0. If number 1, the constant a is 0, this means that the right side is 0 everywhere inside the well. And this obviously violates the normalization condition on the wave function, because the normalization condition says that the total probability must be equal to 1, and is therefore the case of no interest, because zero wave function means no particle inside the box. The second case, with non-zero values of constant a, the right side of equation 11 can be 0 if the sine function is 0. And this is possible for certain values of the argument of the sine function. That is, if the argument of the sine function, which is k times a, equals n pi. Because we know from trigonometry that for integral values of n, sine of n pi equals 0. So the right side of equation 11 is 0 for n equals 0, plus minus 1, plus minus 2, plus minus 3, and so forth. But on sine function, we have another condition, that is sine of minus x equals minus sine of x. The overall minus sign with a wave function like on the right side of this equation is called global phase. I would emphasize to note the word global phase. And for wave function, the global phase or overall minus sign is of no importance, because we know only the modulus square of wave function is measurable. Therefore, the negative values of n do not produce a new or different wave function. Due to this reason, only the positive values of n are sufficient, and this is the standard followed by every book on introductory quantum mechanics. That is, in equation 12, we set n equals 0, 1, 2, 3, and so forth. In order to distinguish different values of n, I put a subscript with k and write equation 12 in the form k subscript n times a equals n pi, and solving this for the value of k subscript n, I write it as k of k subscript n equals n pi divided by a. Now with this value of kn, the wave function of equation 10 becomes psi sub n of x equals a times sine function applied to n pi divided by a times x. Note that I have put a subscript n with the wave function psi as well, so that the wave function for different values of n can be distinguished. If you carefully observe, there is another problem with the wave function given in equation 14, and that problem is for n equal to 0. Because for n equal to 0, the wave function vanishes for all values of position x inside the wave. And this is again the case of no interest, because this value, because n equal to 0 violates the normalization condition. So to make equation 14 physically meaningful, the n equal to 0 value must be omitted from the set of values of n. With this condition implied, the set of values for n becomes 1, 2, 3, and so forth. Now let us turn our attention towards the unknown constant a appearing in equation 14. We can find its value from the normalization condition on the wave function. According to normalization condition, the integral from minus infinity to plus infinity of the product of the conjugate of wave function times the wave function itself integrated over dx should always be equal to 1, which I have written over here. And if I substitute the values, I can write it as integral from 0 to a asterisk sine function times a sine function d of x equal to 1, where I have taken the complex conjugate of the probability amplitude for psi n star, for psi nx, for psi steric. Since the probability amplitude is a constant, therefore combining asterisk with a would give modulus square of a, and I'm writing that over here, and obviously multiplying the two sine function would give the square of the sine function. And using trigonometric relation, the square of sine function can be written as 1 minus cos of x divided by 2, which I have written in this relation. And that would split the total integral into two parts that I have written in the next step: a modulus square divided by 2 integral from 0 to a d of x minus a modulus square divided by 2 integral from 0 to infinity the cos 2 of cos 2 n pi divided by 2x dx equal to 1. It is straightforward to show that the second integral vanishes for the two choices of the limits on it, and the first integral reduces to modulo square of a divided by 2 times small a equals 1, and solving for capital A we get a equal square root 2 divided by a. With this value of a, the final form of the wave function for particle and inside an infinite potential well becomes psi n of x equals square root 2 divided by a times sine n pi divided by a times x. Equation 15 is the final and normalized form of the wave function for a particle inside one-dimensional infinite potential well. Since this video is getting a bit longer, I prefer to discuss the implication of this wave function on the physics of the particle in video part 3 on the topic of particle inside infinite potential well. So meet you again in the next video on this topic, and don't forget to stay connected by subscribing to Sophie Next.